I want to just go ahead and get started getting into the topics that you want to discuss. So let's just go ahead and make that list similar to what we did last time if you made it to the review session. First off, I've got a couple points that people have questions about that they posted up on D2L. So there's only 2 questions posted. One is simply when you're looking at a truss, how do you know if a member is in tension or compression? So we'll definitely talk about that. That's not going to take very long. So the question is, how do you know if a member is in tension or compression? That's going to be question number 1. And then a couple specific questions about practice exam A, problems number 3 and 5. So I'll write those down. I'll write down exam A.3 and exam A.5. And then you can tell me if there's any other subjects you specifically want to talk about, or as we just talk about these, maybe some other stuff's going to come up, or we can figure it out at the end. But right now, do any of you have a specific topic you want to discuss? Well, maybe let's just think about it big picture. So what's the second exam going to cover? What kind of material? So where do we stop right before we took the first exam? So you were talking about like force resultants, is that what you said? Yeah, so that was kind of the end of the subject matter for exam number 1. We had talked about calculating reactions for a system, but we didn't have that on exam 1. We were a little bit behind, so we stopped short and we said we're not going to make you calculate the reaction at a support, but that's definitely going to be on exam 2. So, you know, if there were 3 problems on the test, it would probably be 1 problem would be like reactions of a system. 1 problem would be like truss analysis, trying to figure out the internal forces in every member of a truss, or maybe specific members of a truss. And then another problem would be kind of like the reaction problem, but looking at frames and machines. And so if you remember, like a truss, all of the members are 2 force members, so we know the direction of the force in that member. A frame or a machine simply has some of those components, but other components are not a 2 force member. So it usually has pins connecting different parts of the machine, and you have to identify, well, which of those do I know are 2 force members, and then you make a section cut right through it. So if there were 3 problems on the exam, and I'm not saying there are, but those are the 3 main topics that we're going to cover. And again, exam number 2 is going to be no multiple choice. There's going to be workout problems with subparts, and there might be a conceptual subpart thrown in here or there, but it's mostly just going to be workout problems really similar to what you've been doing on the homework. So out of that discussion, that big kind of overview of what we're going to cover, does anybody want to add anything else to the topics here to discuss?
Example B, problem 5.
Okay. Example exam B, problem 5. Okay, great. Okay, and again, you know, this is a shortened review session. It's only an hour. I just have a really busy week. But if you have questions, I'll be happy to try to answer as much as I can over the weekend. So you can always post questions and send me an email, whichever way you want to go about it. I've got 2 midterms on Monday, so I got 2 classes kind of vying for my time, but I'll try to be as available as possible remotely. There's also office hours tomorrow for statics as well, so you can also take advantage of that. Okay, so let's just go ahead and get into these 4 topics, and whatever else comes up, we'll try to address it, no problem at all. And so first question is, how do you know if a member, and I'm assuming they're talking about in a truss, is in tension or compression? So maybe you can tell me. So let's just look at a really simple truss. Let's just go ahead and say, okay, so here we're going to do a truss example. And our question here is tension or compression. So if I were to set up a really simple truss, just like a 3-member truss like this, and maybe I have a pin on the left, and maybe I've got a roller on the right-hand side, and let's just go ahead and say that I've got some point load applied vertically at the top joint, can you guess which members are going to be in tension and compression? So if I were to label these joints, let's just go ahead and say A, B, and C. So what do you think about member AC? Is that going to be in tension or compression? Compression. What about member CB? Also compression. And member AB? Tension. That is not how you should do it on the exam or on the homework. So that is exactly right, and we got the correct answer, right? But that is not how you want to do it on the homework, because we almost never see trusses as simple in the real world. When we get into more complex structures, like I've been working with my CE 324 students on, I might have a truss with like 10 different bays, 10 different panels, like 20 different members, all kinds of different loading, and you can't do that at that point. You can't just guess, is it going to be in tension, is it going to be in compression? You've got to let the statics work that out for you. And so we still have to guess, but I'm always going to guess that it's in tension. And if you follow that rule, then anytime you get a positive value for the magnitude of that force, it's going to confirm your assumption. And so if you get a positive force, it means it is in tension. If you get a negative force, it just says that your assumption was wrong, which is fine. That doesn't mean you get the answer wrong. It just tells you that it's actually in compression. And so the way that we would analyze a truss like this, I would need to go, I can start like method of joints right here at this section, or we could even do method of sections if we wanted to. I'm going to assume first that I've got these support reactions. We'll call it AY. We'll call it AX, and I'll call this roller reaction BY. But even if I didn't have those reactions, I could still at least start with the method of joints up here at joint C. And so what does method of joints allow me to do? Well, how many unknowns can I solve for at a given time with the method of joints? Well, I will get 3 equations of equilibrium, but one of them is going to be trivial. And so method of joints would be the procedure of, let's go ahead and only focus on joint C. So it's like I make a section cut just around that single joint. That's why we call it the method of joints. And from that, I can do a free body diagram of just point C. And this is like a particle equilibrium free body diagram. We talked about particle equilibrium before we even started talking about moments way back in like chapter 2. And all that I'm doing is I'm making a section cut around this, and then I'm going to draw this joint C as an idealized like single point in space, so I can draw that on my free body diagram right here. I'm going to call that joint C just a single particle. The dimensions of it don't make any difference whatsoever. And now everywhere that I've made a cut with this section cut through a member, I need to replace that with the force in this member. Now, these are all two-force members. A two-force member is pinned at one end, pinned at the other end, and has no other forces or anything else happening in between the two ends. That's the definition of what we call a two-force member. And again, it's a little bit of a misnomer. When we say two-force member, we just mean there's a force at this end and a force at that end. They're equal and opposite. But really, there's only one unknown as far as the force in that member goes, because we know that the direction of the force has to be in line with the member itself. The only unknown that we have is the magnitude. And I guess you could also say the sign as well too, and that's where this tension compression discussion kind of comes into play. But just from a geometry standpoint, let's assume that this is a, let's say a 45-90 triangle. I'm going to draw the force in member AC coming in or out of this joint C, and so like the direction I know, that's going to be 45 degrees. And it's going to be the same thing for this other member. I know the direction of it, 45 degrees. But what I don't know yet is either like the magnitude of this force, or whether it's going compression, like pushing into the joint, or tension pulling away from the joint. And just like I said earlier, if you don't know what the real force in the member is, if you don't know if it's compression or tension, always assume it's in tension, which means that you simply draw the force pointed away from the joint. It's the same thing over here. And so I can just write this as force AC. I can write this as force BC. And the only other thing that I'm missing here is the applied vertical force P. And obviously, for this to be in equilibrium, there's no way that all of these applied forces and internal forces can all be pointed vertically in the same direction, because all three of these right now are pointed downwards. There's no way that we could reach equilibrium. It would just be impossible. And that's why our answer is going to be negative for the magnitude of both FAC and FBC. And if we were to go through the math just really quick, so if I were to sum the forces vertically, I'd get two unknowns. And we can just do that really quick. If I sum the forces in the y direction equal to 0, if I have my coordinate system over here, I would get minus P minus FAC times sine of 45 degrees minus FBC times sine of 45 degrees. So at this point I've got two unknowns. I don't know FAC, I don't know FBC, and I only have one equation, so far it's not really helping. I probably should have first done the sum of the forces in the y direction equal to 0, but no harm if I didn't, because I can always just double back and use this equation later on. So now I'm going to try out the sum of the forces in the x direction, and all that tells me is that there's some x component to this force in member AC pointed to the left, and that's going to be negative because it's pointing to the left. So minus FAC times a cosine of 45 degrees. And then on the right-hand side, I get FBC, the horizontal component of that, in the positive x direction. So that's times cosine 45 degrees. This one simply tells me that FAC has to equal FBC. So again, still two equations and, two unknowns and one equation here, but I can take this relationship that these forces have to be equal to each other, and I can plug that back into this equation up above. So if this is like equation number 1, and then this is equation number 2, I can simply combine those together, and so I can take every place I see FAC, and I can plug in a value of FBC. So I would get 0 equals negative P minus FBC times sine 45 degrees minus FBC again times sine 45 degrees. And I would simply get that FBC equals P divided by 2 times sine of 45 degrees. Now, what I'm missing here, importantly, is that there's going to be a negative sign out in front of that as well, too. All of these terms are negative, so if I brought FBCs over to the other side, they become positive. And so importantly, I do get a negative symbol in front of P. And what this tells me, to kind of go back to the question about do we know if this is in tension or compression, is that if P is a positive value, if it's like 10 kips going downwards, because this is already showing downwards, if this was 10 kips, I would get negative 10 kips divided by 2 times sine 45. I would get a negative value for FBC, which simply tells me that it is going to be in compression. If I got a positive value, I would know that it's in tension, because all the negative value is telling me is that, hey, you guessed the wrong direction. This force is not actually going down and to the right, it's going up and to the left. In other words, it's going up towards the joint, meaning it's pushing on the joint, which is what a compression member does. So the fundamental rule is you have to just blanket guess tension every single time, and if you get a negative value, it just means it is in compression. If you get a positive value, it means that it's actually in tension. Now, the next step would be, well, when I'm done with this joint right here, maybe I want to jump down to this joint and do a free body diagram. And this is where I think people can get a little bit confused, because now if I do a free body diagram of joint B, which is right here, I'm going to have my support reaction By. We haven't calculated it yet, but we could have calculated it from the global free body diagram. And I don't know what the force in member AB is yet, so I'm going to guess the force in member AB is in tension. But the force in member CB, or BC, whichever one you want to call it, I know it's headed in the BC direction, and now I actually could have calculated it and known what the magnitude is. And so I can draw that as P divided by 2 sine 45 and not put a negative symbol on it if I show it pointed in the correct direction. The actual sense of that member is in compression. So I've drawn it in the correct direction, which is compression, and I gave it a positive magnitude. This step right here where you, after you've calculated it, you show the force in the actual direction it's going with a positive magnitude. I think some people get stumbled on that step, but just remember, this is exactly equal to saying that force is going away from the joint, but has a magnitude of minus P divided by 2 sine 45. These vectors are equivalent, right? Pointed down and to the right with a positive magnitude is the same thing as saying pointed up and to the left with the same but negative magnitude. So any questions about that? Just assume tension if you don't know what the force is. Once you know what the force is, you can draw it in the correct direction with a positive magnitude, and then you should be okay. And again, even in my junior and even my senior level classes as well too, people inevitably want to look at this system and say, oh, I'm pretty sure FAC and FCD are in compression, so I'm going to draw these forces, pointed up towards the joint, which is valid, which is completely valid. You can assume that this is in compression and you can draw it that direction. But then when you get a big, huge table of members and you're writing down what the force is and whether it's in tension or compression, you're inevitably going to forget, well, what did I guess? Did I guess it was in compression, and so a positive value means compression, or did I guess it was in tension, so a positive value means it's in tension? And you're inevitably going to forget about it. And so just to keep things easy, even though you know it's not the correct direction, just assume tension, which means you draw the arrow away from the joint, and I think that's going to make your life easier. All right, so any follow-ups on that? Okay, so I think we've gotten the tension or compression taken care of. Let's take a look at example A, problem number 3. So these are all longer workout type problems. Okay, so here is problem number 3. So problem number 3 is it says it's a 2D frame supporting an engine with some mass M1, and that's supported at point G. The frame is pin connected at C, which is kind of this upper right-hand corner, and it's fixed at point D. So even though there's like rollers and everything else here, we don't have any information about the distance or anything else. So it's just telling us to assume that right here it's fixed. Now that's not going to change the answer. If you didn't assume this, it's actually not going to make any difference whatsoever. But just to try to simplify the problem, that was the call of the question. Just assume that here at D there's no rotation, there's no translation. Okay, so with that in mind, draw a complete free body diagram of beam GAC. So let's take a slightly closer look at GAC. So is this a 2-force member? Because I see what looks kind of like a pin over here, and I see a pin definitely over here at C. So I've got pins on either end, so it's a 2-force member, right? Just like a truss? What's the other criteria for a 2-force member? It has to be pin connected at the ends and yeah, the only forces that can be applied have to be at the ends. Which means, what else, why isn't this a 2-force member? Yeah, because this strut right here framing in is probably going to apply a force, right? It's possible, it's completely possible that this might not be applying a force whatsoever, but we can't make that assumption yet until we calculate what the actual force is. So GAC is not a two-force member because it has this intermediate structure that's applying some force, ostensibly not at the ends of the structure. Okay, so as a result, let's go ahead and just draw what our free body diagram is going to look like. I'll draw it over here to the side. So I've got a pin at the far right hand side, which is C. I've got something hanging off point G, and then I've got this point right here, A. So again, for a complete free body diagram, what I'm looking for is all of the external loads, all of the geometry, I need a coordinate system, and then all of maybe the internal forces or reactions as well too, that cross over like that section cut. So again, basically all that I'm doing is I'm making a section cut all around the perimeter. So here's my section cut right here, passing through all of the connecting components on either side. And so everywhere this section cut cuts through, for example, like this cable right here, or this pin right here, or this pin right there, I've got to show what effect that has on the beam at that location. So I haven't shown the geometry yet. We'll go ahead and show that. We just have L1, which is a variable, and we've got 0.35 meters or 350 millimeters over there. Okay, so help me draw the rest of what needs to be shown on this free body diagram. Again, don't worry about the coordinate system. We'll take care of that, or just ignore it for now. Like, what's happening at G? How about that?
Force in the negative y direction.
Yeah, and that force is due to the weight of this motor right here. So technically speaking, you know, we could include like a chain going down on like the center of mass, but with like a quick section cut, we can tell the tension in this cable simply has to be equal to the weight right here. So I can kind of omit that, but we get some weight due to the motor equal to the mass times gravity. And that, again, like you said, is only going to be in the negative y direction, pointed downwards because it's an acceleration due to gravity, and that points towards the center of the Earth. Okay, anything else at G?
Would there be something in the x direction?
Yeah, so it's kind of unclear here. So this is a pin, but it's connected to a cable. And so even though a pin can transfer forces horizontally, the only force being applied here is through this cable, and the cable can only transfer a force in the direction of the cable. So you're absolutely right. A pin can support forces in any direction, but here we know it can only be transferring it vertically because there's no way this cable could put a horizontal force on it.
So if we were unsure, would it be safe to assume that there was something in the x direction?
I don't think that it would be safe to assume because then you'd have too many unknowns at that point. So I think it's something that you couldn't conservatively include because then you wouldn't have enough equations to solve for it. All right, so the same kind of thing happens at point A because I've got a pin connecting this member AB to beam GAC, and so this is a pin right here at A, so do I draw a vertical force and a horizontal force? Or like, how about this? How many unknowns do I have in terms of forces framing in at A? I hear 2. So the pin, it can transfer a horizontal force and it can transfer a vertical force, which doesn't necessarily mean there's 2 unknowns because we just looked over here at G, and why, even though the pin can transfer a horizontal force, why did I only show a vertical? Because the cable can only transfer a vertical force, right? So what can you tell me about this member? Yeah, because this is a 2-force member. This meets our criteria even though beam GAC doesn't. This is pin connected, and there's no forces applied in between the ends. So because this is going to be a 2-force member, I know there's only one unknown, and that's going to be some force in member AB. And then we need to do a little bit of trig, maybe like law of sines or law of cosines to figure out this angle right here. I'll just call this theta BAC. Again, there's always a possibility of like a law of sines type problem here. And I know the length of this side, I know the length of this side, and based off this angle theta, I could calculate at least one of the angles. And so you can figure out the angle here of this vertex at A using either law of sines or law of cosines. So you have enough geometric information to figure out this angle right here, and so this is the orientation is a known value. Now here I assumed that this member is in tension. Is it going to be in tension? No. It's going to be in compression. As this weight comes down over here, it's going to have to be pushing back up, which means it's in compression. But that's fine. I'll just get a negative value, and then I'll be able to say FAB, that member AB is in compression. Okay, now what about the pin at C? All right, so before I was dealing with the pin at G connected to a cable, a pin at A connected to a strut, like a two-force member. Now this pin at member C, how many unknowns am I going to get there? I heard 2, I heard a whisper of 2. Are we confident 2 unknowns at C? Right, it is connected to this member CBD, which is a continuous member. Right, this pin right here is just the way that this strut is attached, but this member is continuous the whole way. And so this is not a two-force member. And plus, even it's not even pinned at the other side anyway, so it doesn't even make a difference. So this member right here isn't an axial force member only, which means that I have some unknown force Cx, some unknown force Cy. Okay, so can you solve for FAB, Cy, and Cx using this free body diagram? And again, we'll make it complete now. I'll give a coordinate system. But is equilibrium enough to solve for this? All those unknowns. Yeah, you need some trig. I know this value. I can calculate the weight based off gravity, which I know, and the mass, which I've been given. I know the angle, so that's not an unknown. So I really just have one unknown, which is FAB magnitude, unknown magnitude of Cy, and the unknown magnitude of Cx. 3 unknowns, and I will get 3 equations of equilibrium. Right? My moment equilibrium equation is valid here. This isn't like the method of joints, because why? Why do I get a moment equilibrium equation here, whereas I didn't get it for like moment of joints? Well, so the question is there a point that all of the forces don't intersect at? And if there is one, then you can use the moment equilibrium equation. So like, we can just look at point A right here. So point A, Cx goes through it, but this force doesn't, and Cy doesn't go through point A. And so I've already found one point where not all of the forces intersect, and so I could sum the moments about that. That's all you have to find. But with the method of joints, all of the forces by definition are going to go through the same point. So moment equilibrium is never available. But if you're using like method of sections, kind of like what we did right here, and you can find a point where not all of the lines of action of the forces intersect, you can use moment equilibrium. So I could have some of the forces in the x, some of the forces in the y, and some of the moments wherever I want. Now A would be a pretty nice spot to sum the moments about, because what unknown would show up in that equation if I sum the moments about A? Yeah, Cy, FAB won't because it passes right through A. What about Cx? Yeah, its line of action passes right through point A as well. Now, I already know W, and it doesn't pass through A, which is good. And so that tells me that Cy and W are the only forces that are going to show up in that moment equilibrium equation, and I know all the geometry, so I'd be able to solve for Cy directly. All right, once I have Cy, I could sum the forces vertically. I could solve for FAB. Once I have FAB, I could sum the forces horizontally, and then I could calculate Cx, I'm sorry. So once you get one of them, usually using the moment equilibrium equation, then it kind of unravels the rest, and you can start using some of the forces, or if you want, some of the moments to get the rest. Any lingering questions about this free body diagram, or kind of the process of how you would start solving for them? Okay, so the other subparts to this problem, just to kind of talk about them quickly, determine the force in member AB and all the forces transferred by pin C. We just talked about how to do that. That's relatively straightforward. Again, I think the trickiest part for some people is just the trig. Okay, it says ignore the weight of the engine. If the maximum force that strut AB can support, is 35 kilonewtons, calculate the maximum vertical force that the frame can support at point G. So it's saying ignore the weight of this engine, pretend it's not there, and if the maximum force in this member AB is 35 kilonewtons, how much force can I apply at point G to arrive at that maximum force in AB? All right, so we'd go back to our free body diagram for that. And tell me, how could I formulate an equation that would allow me to isolate just the force at G? So now we're ignoring the weight. Just some force at G and the force in member AB. How could I make an equation that directly relates this force to this force? So if I sum the forces in the y, it's a good guess, but Cy is going to show up. And I don't care about Cy. All I care about is FAB and FG, because I know what FAB is now. I know FAB is 35 kilonewtons, and I want to figure out, well, how big does that make FG for this to be in equilibrium? So I think sum the moments about C, that gets rid of Cy, that gets rid of Cx, and it basically tells me that only the component of FAB in the y direction, because FAB in the x direction would be coincident with C, just whatever the vertical component of FAB is times this distance has to counteract whatever this force FG is times the overall distance between G and C. So I can write that equilibrium equation. So again, this is like part C. So if I were to sum the moments about A equal to 0, I would get the force at G that we don't know yet times L1 plus 0.35 meters, and L1 is given to you in the problem, and then plus FAB in the y direction. So we can just say FAB times sine of theta BAC times 0.35 meters. And now I know what FAB is. That's 35 kilonewtons. And this problem wasn't specific about compression or tension. I'm still assuming tension here. And so I just put in 35 kilonewtons of tension. That's not going to change the magnitude of my answer for FG. It's just going to change the sign. So if FAB fails at 35 kilonewtons of tension or 35 kilonewtons of compression, it's not going to change the magnitude of FG. It's just going to change whether it's going up or going down. So to that extent, it's really inconsequential for the problem whether you assume FAB's in tension or compression, because all it will do is just change the sign of FG. Yeah, Max?
Sum the moments at C.
I'm sorry, sum the moments at C. Thank you. I'm so used to summing them about point A. Was there another question over here? Okay, so that's the relationships, and again, generally speaking, you're almost always going to have to resort to the summing the moments about some point, and I recommend doing that early or first. It won't give you the wrong answer if you started summing the forces in the y. First, it's just going to give you an equation that you wouldn't have enough information to solve for, or you would need to do a couple simultaneous equations to get to the same answer. So it's not about right or wrong method, it's just like which is more efficient to get with like a single equation to how you want to analyze that relationship. Because again, what were we looking for? We were looking for a relationship between FG and FAB, and this is the most efficient way to do it. It's not to say it's the only way to do it, but it's probably the most efficient. So that's part of kind of this process as well too. All right, any lingering questions about this crane type problem? Okay, so let's go back to review. So I think we've taken care of exam A3. So exam A problem 5. Oh yeah, I love these problems. The good thing is for you, you don't need to worry about stability, determinacy. We talked about it and we kind of made it half of a lecture's worth of discussion. And I said, this is good background for you to have, and we'll actually talk about it again in EAS 212. And if you're in civil, we'll talk about it again in CE 324. Stability and determinacy, we're basically trying to figure out, number one, is statics enough to solve for all of the unknown reactions? And that's what we call determinacy. And then stability is basically saying, is this system going to start moving based off the condition that it's like currently in? Or if we were to apply like a force to it, would it start to deflect even if everything is like a rigid body? And so we talked about it for maybe 40 minutes a couple of weeks ago, and you don't need to worry about it. And this was a conceptual question, and this is a really tough kind of a conceptual question, so I wanted people to start looking at it and drawing free body diagrams, splitting it up into multiple different segments. But last year we just had more time to talk about it. But we'll revisit this topic later on, but not on exam 2. So just don't worry about it at all. Those are the easy ones to deal with. But this is a really good question. I'd love to be able to ask it of you guys, but it might just have to wait until strengths. And then from here, we had a question about exam B. Problem number 5. And yeah, so I tried to kind of identify for these where what's going to be covered on the exam. I just missed that last one. But here, if we get to B5, oh yeah, this is a good one. Another good one. Okay, so we would call this like a frame or a machine as well too. Very similar to that crane that we were looking at a second ago. Okay, and it even says the frame. So the frame to the right is subjected to a couple moment at A as shown. So let's just stop right there. A is a pin. Can I apply a couple moment to a pin, like the location of a pin? Because I've told you a million times, look, a pin cannot like support a moment. So does this even make any sense, this first sentence? It does, because what a pin cannot do is like transfer a moment from this system down to the support, or vice versa. It can't provide like a moment reaction as the nature like of that support. It can transfer a force left and right. It could transfer a force up and down. But if that beam AB wants to rotate, that pin has no resistance to that rotation. Now that's not to say we can't like stick a key into that beam right at A and twist on it. It just means whatever's going to be resisting that twisting at A is not going to come from that pin. It's going to come from some other place over here. Okay, so first sentence we said, it seems a little bit weird, but an applied moment at a pin, completely fine. And so I've got my couple moment applied. The smooth roller at C is supported by member AB. And we haven't really seen this before, and so this is kind of taking you out of your comfort zone. And so it asks us first, it says assume members A, B, and CBD are weightless, but that the roller at C weighs 10 pounds. Okay, so at this point, it's a relatively complex system. How do you want to break this up into manageable, like free body diagram or free body diagrams? What will we do with a system like this to maybe divide and conquer?
Could you sort of C?
Well, there's actually, so there's actually a couple of different things that we could do. So this actually appears to be determinate even if we don't make a section cut. So if I were to just turn this into a free body diagram, we can have AY, we can have AX, and then the roller here at D is really the only other support. And so here, this would be, I'll just show it to the right as well too. Doesn't matter. If we guess the wrong direction, that's fine. I'm trying to get into the trend of showing everything just in like the positive X and positive Y, just to make the equilibrium equations a little bit more straightforward. And so I've shown all of the reactions either in the positive X or the positive Y. You don't have to do that, but I think it makes the equilibrium equations a little bit easier to not to worry about one less thing in terms of signs. But so here, how many unknown reactions do I have? Yeah, shown right here. So this is like I've just made a section cut through the pin. I went all the way up around. I made a section cut through the roller at D. And so everywhere that I've made that section cut through the supports, the external supports, I just drew what that reaction is going to look like. And so 3 unknowns. So with this global free body diagram, I can solve for all of the external reactions, which is great. But is that going to get me the answer to part A? Part of the way, right? It's going to get me, actually, I'm sorry, for part A, it's going to get me all of those reactions. Now, for part B is where we can't rely on the global free body diagram, and we need to start looking kind of inside. So here, I've already, in part A, the global free body diagram has gotten me the vertical reaction, has gotten me the horizontal reaction, both at the pin at A and at the roller at D. And so global free body diagram was enough for part A. Part B is trickier. Determine the forces transferred by the pin at B. So now I need to start making some section cuts, and the question is going to be like, what should my section cut look like to isolate what the forces are transferred at B? So I know I've got to make a section cut through B at some point. Okay, so I've made a section cut there. Where should that section cut go? Like up through this member right here? How many unknowns do I get just from this cut right here through the pin? 2. Is member AB a 2-force member? Right, it's pinned and it's pinned. I mean, this load is applied just at A. Why is it not? Yeah, because of this roller. This roller is pushing down. And actually the one thing that we figured out on the previous free body diagram is that there is some additional weight being applied. The weight of this roller is 10 pounds. So sorry about that. But same thing is going to be applicable here. Weight equals 10 pounds. But so there is a reaction between the roller at C and this member AB. So AB is not a 2-force member, which means there are going to be 2 unknowns, 2 forces transferred by the pin at B. Well, we need to finish our section cut basically. So if you're telling me I get 2 unknowns from this part of the section cut, I've got to continue that on and completely separate and have 2 different sides of my section cut. So do I want to continue my section cut like that? What happens if I were to cut through this member CD? How many unknowns am I going to get if I make a cut through CD? I'll get 3. So then I get 3 up here, I get 2 down there. That's going to be 5. That's not going to work. Okay, what if instead I make my section cut like that? and I go through member AB. How many unknowns do I get for that section cut? Yeah, still 3 more, because this is not a 2-force member. This is not like a truss member. It's not just an axial force. It could have a shear. It could have a bending moment inside of it. So I get 2 here plus 3 here. It's not going to work. Okay, all right. So where am I going to make my section cut? I can't go up. I can't go down. Yeah. What if I go horizontal here and right through there? Can I do that? What direction? I mean, this interface right here, a roller sitting on top of a flat surface, what direction is that force between them going? Or how many unknowns do I have being transferred on that surface? Well, how about just a regular roller like this roller right here? I mean, this is a roller rolling on a flat surface. How many unknowns did I get? 1, right? Just the horizontal, just the perpendicular to the surface that it's rolling on. So the force in between this interface is going to be just a force going up or down. And so now, if I want to, I can keep either side of the section cut that I want now. Either one will only have 3 unknowns on it because I've already solved for all of the reactions. So I can choose either the top that looks like this, and there's my pin right there, and here's my roller right here. So I would still have dx, the reaction, and now I'm going to have some unknown force, bx and by, being transferred by that pin. I'm going to assume to the right and upwards here, and then the only other force that I don't know, I'm going to assume that there's compression between those two. I'm sorry, that's not the only force left. I'm just going to call that Cy, excuse me. And what other force am I forgetting about here?
The weight.
Yeah, the weight of that roller. It's just being applied at the center of gravity of the roller itself. And so here I also have this weight of 10 pounds. And so I know dx, I know the weight, I know all of the geometry. I'm just not drawing it on here, but I know it all. Can I solve for Cy, By, and Bx? 3 unknowns. How many equations of equilibrium do I get? 3. Is moment equilibrium trivial here like it is with method of joints? It's not trivial, it's worthwhile because I could find a point, like for example this point right here, if I sum the moments about D, not all of the forces are going through that point D. And so if I can't find a single point where everything is being coincident, all the forces are being coincident, then moment equilibrium is not trivial. So here, if I were to solve, or how about let's just sum the moments about B is a better idea. Sum the moments about B, I get Cy, I get W, and I get dx in that equation. I know dx, I know W, so that would allow me to solve for Cy right away. And so you would have enough equations of equilibrium to solve for all of these. Now, what if I chose everything on the other side of that section cut? I have AY that I know. I have AX that I know. And then here, I don't know what BX is. I need to draw it in the opposite direction of what I've drawn up above in order to get the same answer. And so then BY, I'll show opposite of what I did on the upper free body diagram. And the same thing with CY, I will draw that opposite of what I did for the top free body diagram. Now the only reason I'm doing that is just to get, if I were to use either free body diagram, as long as I show these forces along the interface is equal and opposite, I'll get the same exact answer, same exact sign, regardless of which one I use. But back to the question again, I know all of the geometry, I'm just not drawing it for time's sake. I know AX, I know AY, I don't know CY, I don't know BY, I don't know BX. Do I have enough equilibrium equations to solve for these 3 unknowns? Absolutely. And so the trickiest thing about this problem is this section cut through the roller. We haven't really done that before. And then the couple moment I think can throw some people for a loop. But fundamentally, I mean, these steps right here, other than just being clever about where you make that section cut, it's all the same steps that we've been doing before. And you know, some people get a little bit paralyzed by choice right here, but you can choose either everything above the section cut or everything below the section cut, and you'll get the exact same answer. Yeah, Max?
Why didn't you actually include the weight in the section?
Oh, great question. Yeah. So the weight is not included because it is applied at point C, at that center of mass of point C. If I were to have made like a section cut through half of that roller, I'd have to include, you know, just a proportion of that mass, but we don't know how to deal with that quite yet. Now, am I ignoring that weight when I look down at this free body diagram? Let me say I'm not ignoring it, but where is it showing up down here? Well, we're trying to calculate CY, so you're right, it's going to be part of CY, but where is it in the values that I've already calculated before I even try to calculate CY? This is kind of like our discussion about when we're looking at a beam and we make a section cut and we choose, say, the left side. I'm not ignoring all the loads on the right side of the section cut because they get implied in these support reactions right here. So like this support reaction AX and AY, part of that is due to the weight of that roller. So it's not like it doesn't exist, it's just that we're only looking at the effects of it as it gets imputed to point A. All right, so any last minute questions before we transition to my 324 class?
Probably don't have time with section cuts through numbers.
And the good thing about the exam is that the only section cuts that you're going to need to make through a member would be through a pin or through a truss member. So you're not going to have to do like moments and shears or anything like that. It's only going to be axial forces or just the forces transferred by a pin. And so the material that we went over this week with section cuts to figure out the internal resultants, that's going to be on the final, that's not going to be on exam 2. So the only kind of section cuts that you need to make for this exam would be like a section cut through a pin, or if I had a truss, right, like a section cut through one of those. But every time you cut through a truss, you just know the direction of the force is in line with that truss member itself. So I'll be available by appointment. I'll try to answer as many questions on the discussion board as possible. But hopefully this was helpful covering some of these big topics, and use those discussion boards, and I'll try to answer as many questions on there as I can. Otherwise, I'll see you all bright and early on Monday morning.